In this module, we are going to introduce the concept of discrete time Fourier series. We are going to learn this concept in analogy with the continuous time Fourier series. The comparison or the analogy with the continuous time Fourier series will help us to understand the things in much a better way. Let us start with the recap of how we have represented the continuous time periodic signals. So on the left, I am writing about the continuous time periodic signals. So we have that the continuous time periodic signals we know that for continuous time periodic signals, a signal is said to be periodic if it repeats after a certain duration of time. So let x of t be a signal that is periodic in nature, and it is said to be periodic if it repeats after a certain duration. So let x of t plus t naught, where this t naught is the fundamental period of this x of t. So this t naught is the fundamental period given by t naught equals to 2 pi by omega naught. That's the fundamental period. Similarly, for the discrete time case, we can define equivalent periodic signal. So for the discrete time case, discrete time, a signal is said to be periodic if it repeats after a certain number of samples. So that means if x of n is a certain signal that is periodic, that signal is going to repeat after a certain number of samples. So x of n is going to be x of n plus capital N naught. Now the duration here that we are going to use, or the number of samples that we are going to use, is n naught instead of t naught here in the continuous time case. So this n naught is the equivalent period or the fundamental period for the discrete time periodic signals, that is given by 2 pi by omega naught, the small omega naught. Now we have defined the complex exponentials for the continuous time case. So let me write that. For the continuous time case, we have the complex exponential been defined as, let me write that, the complex exponential are given by e power jk omega naught t. What is omega naught? Omega naught is the fundamental frequency that is given by 2 pi by t naught, where t naught is the fundamental period. Similarly, we can define the complex exponential for the discrete time case. So for the discrete time case, the complex exponential is going to be, complex exponentials are going to be e power jk. Now instead of capital omega naught, we are going to have small omega naught, and instead of small t, we need to have this small n, just because this time is discrete in nature, where this omega naught, the small omega naught, is going to be 2 pi by n naught. You can see the clear analogy between the continuous time and the discrete time representation of periodic signals. Now, in order to represent the continuous time periodic signals, we have said that they can be represented using a set of harmonically related complex exponentials. That means we said that any periodic signal, let it be xt, so let me write that for the continuous time case, this we have already seen that xt, if it is any periodic signal, we have said xt or xp of t can be represented as a set of a combination of a set of harmonically related complex exponential, that is jk omega naught t, where this k is running from all the way from minus infinite to infinite. Similarly, we can define the representation for discrete time case. Now for the discrete time case, the representation would be x of n equals to summation ok x ak e power jk small omega not n. Now we need to think about this range of k here. You can see that this range of k is going to be different for discrete time case. Now why is that? If you observe the complex exponentials for the continuous time case and the discrete time case, we can see that for the continuous time case, as we vary the value of k, we get distinct signals, distinct complex exponential signals. So if we change the value of k, we are going to get different complex exponential signals. Whereas for the discrete time case, if we vary this k, we see that these complex exponentials are going to repeat after a certain value of k. Why is that? Because this k here, if I increase or if I change this k after a certain value, let this k be some value plus n naught, then this complex exponential is going to repeat. What I mean to say here is that, let's suppose this complex exponential, if I add a value of n naught to k, so let's say j omega naught n, and instead of k I'm writing k plus n naught. So I'm taking an integer such that it is k plus n naught, where k is an integer and n naught is the period. You can see that this expression and this expression is the same. Just because this e power j omega and omega naught is 2 pi by n naught. So this omega naught is 2 pi by n naught, and because of this capital N naught in the denominator and in the numerator, here the numerator and denominator gets cancelled, and that will lead to e power j integer multiple of 2 pi, that is going to be 1. So it will boil down to the same expression, that is e power j k omega naught n. What does this mean? This means that this k is having a limited range, and that too the range is defined over n naught. So this k is not varying from minus infinite to infinite as was the case for the continuous time, but here the k varies in a range of n naught. What do I mean by that is k here could be any value in the range of n naught. That means k could be, let's say, from 0 to n naught minus 1. You can see that there are total number of n samples here. After n samples, this k is going to repeat, just because this complex exponential is going to be unique only for the range of n naught. Or you can take the range of k from 1 to n naught, or from say 2 to n naught plus 1, 3 to n naught plus 2. Any range of k within limits of n naught is fine. So this is the main difference between the representation of continuous time periodic signal and a discrete time periodic signal. The complex exponentials for the continuous time are going to be different for different values of k, whereas for the discrete time the range of k is limited. In fact, that is equal to the range of n. You can see that the small n here, that is the discrete time instance is going to have the range from 0 to n0 minus 1. Just because this signal is repeating after n0, the range of small n is from 0 to n0 minus 1, or any range in n0. So I am saying that this n0, this small n, is defined in a range of n0, and so is small k. This is also in the range of n0. You can see that if this range of k or n exceeds n0, then the signal, the exponential is going to repeat. The signal is going to repeat. So the representation that we have obtained is the Fourier series representation for the discrete time case. So here the expression that we have obtained is the Fourier series representation for the discrete time case. The only thing to note is the range of k here. Now, as we have obtained the expression for a case for the continuous time case, we can obtain the same for the discrete time case. So let's suppose we have, again in the same analogous pattern, we are going to derive the equation for a k. So let's suppose on the left I have the continuous time, and on the right I have for the discrete time. For the continuous time, we have seen that, let me write that, for the continuous time we said that this signal x of t that is represented as a set of complex exponentials, that is x of t summation a k e power jk omega naught t, where this k is running from minus infinite to infinite. We have multiplied both the sides of this expression with the exponential that is a complex conjugate of this exponential here. So that means for the continuous time case, we have multiplied both the sides by e power minus j and a different integer there, so let it be p omega naught t. And if you can recall that, and we have integrated, and integrating over a period t naught. Similarly, we can do for the discrete time case. So let me first finish this for the continuous time case. So the expression is going to be something like this: x of t being multiplied as e power minus j, instead of k I am using this p omega naught t, and this equals to summation k running from minus infinite to infinite ak e power jk omega naught t, and this whole thing is getting multiplied by e power minus j p omega naught t. And this, let me make a space here, and in addition to that we are integrating both the sides over a period. So let it be from 0 to t. Similar things we can do for the discrete time case. For the discrete time case, we have x of n being represented as summation over k, where k range is over a period of n naught ak e power jk omega naught t. So this, instead of omega naught t, we have the small omega naught n, just because it is a discrete time case, and we apply the similar kind of operation here. So we multiply both sides by a complex conjugate of the exponential term. So let it be e power minus jk. Instead of k, I'll be using another variable. Let it be p omega naught n. And now we can see that we have integrated both the sides just because it was a continuous variable there. Now for the discrete time case, we have the discrete variable. So instead of integrating, we need to sum over a period. So we would be summing and summing over a period of n naught. What we are going to obtain is analogous to the continuous time case. So we would have on the left summation over a period. So let that summation be ranging from any range from 0 to say n naught minus 1, or any range in n naught. So that is going to be equals to summation over a period of n naught. So this n is going to be over a period of n naught, and this is x of n being multiplied by e power minus jk omega naught. Instead of k, I'll be using p here, p omega naught n equals to summation over a period, let it be over a period of n naught. It is going to be summation over a period of k, again n naught ak e power jk omega naught n. You can see that this expression in the parenthesis is the same here. We have simply multiplied both the sides by, so we have left with the exponential here. It is going to be whole multiplied by e power minus j p omega naught n. So let me write that on the next line, being multiplied by e power minus j p omega naught n. You can see that we have simply multiplied both the sides with this complex exponential and have summed it up over a range of n naught. Now we can see that for the continuous time case. Let's move on to the continuous time case. As we have integrated both the sides, can exchange the rule of integration and summation, so we can take this inside. Similarly, for the discrete time case, we can take the summation inside. As we know that the summation is over n, so it will be only over the variables which have small n there. So the expressions are going to be, so now next page I'll write the expressions. On the left we have for the continuous time case, so the expressions are going to be as we can see that if we exchange this integration and summation, if I take this integration inside this summation, that is going to give you integration 0 to t, or over a period of t. I'll write it in general, over a period of t or t naught, you can say, x of t e power minus j p omega naught t, that is going to be equals to summation k ranging from minus infinite to infinite ak. Now I have taken the integration inside, so it is going to be integration over a period of t naught e power. You can see that from the previous expression, that is going to be this exponentials when multiplied. You can take this j omega naught t common, and that is going to give you k minus p. So that is equivalent to e power j k minus p omega naught t. Now what about the discrete time? You can see for the discrete time case, if we take this summation inside, what we are going to get is the summation. On the left we have the small n here, which is running over a period of n naught, x of n e power minus jp small omega naught n equals to summation. Now we have exchanged the summation, so now we'll have for k and this ak, and we have another summation inside, that is over n. So that is going to be e power j k minus p omega naught n. Can observe the analogy between the continuous time case and the discrete time case. We are proceeding in the same way. This we have already calculated, we have already solved these equations, but still for the sake of analogy we are presenting them once again. You can see the clear analogy between the continuous time and the discrete time representation of Fourier series. Now for the continuous time case, we have solved this, and we say that this integration, the integration here that we have seen, is going to vanish. It's going to vanish when k is equals to p, and that is going to give the value. So let me write that this integration inside the parenthesis, inside the brackets, so over a period e power j k minus p omega naught t, you are going to get equals to capital T naught if k is equals to p, or it is going to be 0 when k is not equals to p. We have already seen why is that. When k is p, k is equals to p, we are left with t naught, because the exponential to the power 0 is going to be 1, and we are left with only the period t naught. And if k is not equals to p, so it should be p here. When k is not equals to p, so it would be some integer multiple of 2 pi by t naught, and that is going to give you 0. Now let us see what is going to be the case for the exponential in the discrete time case. So let's consider the case for the discrete time case. So for this exponential in the parenthesis, so we have here the summation over small n, that is e power j k minus p small omega naught n. Now similar to the continuous time case, this is going to be equals to n naught when k is, so this is going to be n naught when k is going to be, you can see that from k is equals to p, k is equals to p, so the exponential is going to be 0, exponential to the power 0, and that is going to give you n naught, whereas it is going to vanish if k is not equals to p. Now hence we have obtained for the continuous time case. Now let's go to the continuous time case. Because of this, each value of this ak, so this ak, therefore you can see that this term here, this term is going to be t naught only for k equals to p. So I can take this t naught outside, and therefore this ak for every value of this a, for different values of k, it is going to be equals to, now this t here I am going to shift on the other side, so that is going to give you 1 upon t naught integration over a period t naught x of t e power minus jp omega naught t dt. So we have forgotten this dt here, dt, and of course in the previous slide this dt is missing here, so dt, of course dt, yes. Similarly for the discrete time case, we have this ak, ak equals to, now for the discrete time case, as we have this term in the parenthesis as n naught, I'll shift that term on the left, so that is going to give you 1 upon n naught. Instead of integration, we are going to get here the summation over this n naught, so let me write that over n naught x of n e power minus j p. Now p is equals to k, so I can replace that p as k. So in the continuous time case I am going to repeat, and also for the discrete time case, so that is going to be, instead of p I would write here k, just because they are the same, j p omega naught n. You can see the analogy between the continuous time case and for the discrete time case, they are very closely related. So let me highlight this equation. These equations that we have obtained on both the sides are the Fourier series coefficient equation for the continuous time and the discrete time case. On the left we have for the continuous time case, and for the on the right we have for the discrete time case. You can see that the procedure remains the same for deriving this equation for the Fourier series coefficients as was the case for the analogous for the continuous time case. And in the beginning we started off with this the Fourier series representation. So on the left we have for the continuous time, and for the discrete time I have on the right. So you can see that for the continuous time case, it is the set of harmonically related complex exponentials, as is the case for the discrete time. Similarly, the coefficients that are AKs, the Fourier series coefficients, we have 1 upon t naught integration over period xt e power minus jk omega naught t, whereas for the discrete time case we have ak 1 upon n naught, so that is the period, or a summation over a period of n naught, just because this is a discrete time signal, xn e power minus j. Now instead of p I can write it here k, just because both of them are the same. So instead of p I would write here k omega naught n. We shall see more into this in the next module. Thank you.